All right, thank you, Luke. Good day, everybody. As Luke mentioned, my name is Vincent Britz, or Vince. I work at Flownex, and I work in the high-level technical support as well as some of the development work as well. Today, I'm going to be talking about controller tuning. So, just to kick off with a small overview, today I'd like to talk about some of the basics of controller tuning, just cover a little bit of the theory involved behind it, and then discuss some of the tuning techniques. Then I'd like to demonstrate a tuning technique when we're tuning a tank level controller. And then finally, I'm going to highlight some applications of simulation-based controller tuning, so some practical examples where this can be used. All right, so to begin, control system in a plant, be it a processing plant or perhaps a generation plant or something like that, is the nervous system of that plant. Nowadays, manual control is out of the window. People don't operate valves by hand anymore. Everything is done digitally. So the control system itself is integral to the performance of this plant. What this means is that poorly tuned control systems severely impact the performance of this plant. Oscillations in process conditions result in processes having to be turned down slightly to ensure that maximum limits are not reached. This results in reduced production and reduced efficiency of these plants as well. So properly tuning these systems can increase the efficiency, reduce your energy costs, and increase the production of your plant. However, when it comes to actually tuning these control systems, it's difficult to do while the plant is online because you need to do characterization tests of the control system. Historical data isn't good enough to do this, so you have to shut the plant down, do tests on the plant, and then restart the plant afterwards. This then becomes a large financial offset and just kind of discourages the practice of then tuning an existing control system. So what I'd like to present is then Flownex. Flownex is a thermodynamic simulation environment. What that allows us to do is model the process in our thermal fluids library. This includes everything from tanks to pumps to compressors, turbines, any type of thermal fluids related components, as well as the control system. Today I won't be spending much time on the thermal fluids at all. The focus is on the control, and we have two different types in our control library. We have digital control as well as analog control. The digital control is typically high-level control at the DCS level, where basically decisions are made inside of the control system. This is adjusting ramp rates based on transfer functions, or turning on or turning off systems based on load requirements. It's very much logic structured, Boolean control, if you would call it that. And the other type of control is analog control. This is your PIDs, processors or controllers that receive an analog signal. Based on that, compute a control output. And these controllers themselves need to be tuned. These controllers themselves typically have many different types of algorithms. So we have an interactive, a non-interactive algorithm, as well as a parallel algorithm. And depending on these algorithms, you would use different tuning techniques, but ultimately you still need actual constants for these controllers. These are the settings for the controllers. You have a proportional term, an integral time, and a differential time. Sometimes you might see it represented as an integral constant and a differential constant, but they basically represent the same thing. To actually solve for these values, or to input these values, you need to sort of characterize the process. These terms will have an effect on how fast the controller responds to an error and how that error is processed in the integral and differential components as well. So as I mentioned, there are these three algorithms, and depending on the hardware that you have, you would be able to link that hardware to one of these algorithms. If it is just a PI controller, you would see the same structure, but just without the differential term. So you could potentially have a non-interactive PI controller or a parallel algorithm PI controller. But in essence, the logic is, or the structure is the same. So when it comes to tuning these, you have a couple of different tuning techniques available. The most common ones that people speak about in controller tuning is Ziegler-Nichols and COHEN-COON. Lambda tuning is also relatively popular. These are just a few techniques. There are many techniques out there. If I just go back to the previous slide, the author who I found these resources at, the website, It's documented by a man called Jacques Smuts, a fellow South African. He has worked internationally with regards to control system tuning. He's done work in Australia, Canada, the United States, and is very, very involved in this and has documented a lot of techniques for different systems. So be it level control or controlling particularly difficult systems. A lot of material has been published. His website is in the form of a blog. I'd encourage you to take a look if you are interested. So like I mentioned, there are a lot of techniques out there. Many of them are discussed online. And all of these techniques have many things in common. They require inputs for the characterization of the controller or of the process. And from that characterization of the process, we can then determine the ideal constants for our controllers. So the graph that you see on the right there is just a typical step test for controller tuning. In this process, what we do is we take our controller output, we make a step test in that. The shift itself just needs to be significantly larger than the noise that you see on the signal. And then we observe the change in our process variable. That is the output from our plants, be it a temperature, a level, a pressure, whatever the value is we're controlling. We then analyze that response, find out our dead time, which is represented by TD, our tau, which is our process time, and then also our process gain. With those parameters, we're then able to calculate the ideal constants for our PRD. So today, I'm going to be speaking about COHEN-COON tuning. This is not particular in any way. The software itself can be used for any type of tuning technique. It's purely just an example to illustrate the functionality. So the table that we see over here is a table that I received from Jacques Smuts' website. Basically, it documents the different formulas you would use for calculating your proportional gain, your differential time, and your integral time. So I'm going to be using a PID controller, so the bottomer of that table, and the inputs are tau, TD, and GP, which are all calculated as I discussed using this step test. So the actual network we're going to be working on is the network that you can see over here. It is a tank with a particular level inside that we'd like to control. That tank is being filled by a pump that's driven by a turbine, and it's being drained through the line at the bottom, which has a valve in it. The turbine itself is driven through steam on the left-hand side, and there is a valve in line with that as well to control the steam flow rate. So what we're looking to do in the system is use a PID to control the level in the tank by adjusting the valve position in that steam line. So there's quite a lot of quite a large delay inside of this side of the system. Adjusting the valve position is going to ultimately adjust the flow rate of steam through that pipeline, which will change the power into the shaft. This will either speed up or slow down the turbine pump arrangement. Then that pump will either increase or decrease its flow rate into the tank, and that will ultimately affect the level inside of the tank. So there are multiple layers to this control network. Flownex itself is very good at modeling the thermal fluids, so we can simply build a network as you see here in the GUI, and then we can focus all our attention onto the controller tuning. If you are interested in the thermal fluids, please contact us or see our website. There's a lot of information on the thermal fluid side of the software as well. So when we look at the control, what we have here is our PID controller. On the left is an analog input. This is simply connected with a data transfer link to the tank on the right. We simply have taken the level output and then transferred that to this analog input and connected that analog input to the process value. So that's simply done by just clicking on the component and linking it to the process value. You have access to all of these other results inputs on the PID itself. And once you've built a network using these control components, it's very intuitive to follow. All of the links correspond to little blocks inside of it, so it forms almost like a control flow diagram, and it's very intuitive to both process engineers and control engineers. So if you end up building a simulation inside here, both engineers from a control background as well as a process engineering background can communicate quite efficiently. Over here we then have a constant linked to our set points. This is just a constant of 3, implying that we would like our controller to adjust the level inside this tank to be 3 meters. And then we have our output over here, which corresponds to the valve position for this valve in our turbine chain over here. So This is simply linked to the actual valve angle. At the moment, the controller is set to, excuse me, let me just set that back. So at the moment, this controller is set to manual. We then will adjust the manual value for it. So at the moment, the manual value is set to 1, and then that will be transferred to the actual valve angle on this valve over here. All right, so like I mentioned, we need to characterize our system. So that step test that I described, we're going to be doing that with the controller in its manual mode. We will then change the manual tracking value to another value and then record the change in the level of the tank over time. To do the step change, what I've done is just simply programmed in an action. It's as simple as just right-clicking, creating a new scenario. We've then created one that will adjust the manual value on this controller from 1 to 30, and then we'll be able to visualize the response of our system. So I'm just going to quickly solve that. I've added the responses to this graph over here. The red line represents the valve position, so it started out at 1, and then we see a step change up to 30. Then the blue line over here represents the level inside of the tank. You can see this level is slowly increasing over time. That's because opening this valve increased the steam flow to the turbine, which increased the speed of the pump, and increased the flow into the tank. So we see the level in the tank gradually increasing until the flow in is matched by the flow out due to the increased pressure at the outlet of the tank. This is due to basically the increased pressure head at the exit of the tank. All right, so now we can see that our process is stabilized. What I'd just like to point out is that our simulation here is running with time steps of 100 milliseconds, and we've just solved just over 700 seconds worth of simulation time. So the software itself is an incredibly fast transient solver and is very stable. It's an implicit solver and requires almost zero user input when it comes to adjusting your flow solver settings. You can run with the basic or the default settings for basically any network. So what we have over here is then our large set of transient data. If we were to do this in a plant, we would be looking at doing step tests that would last approximately 10, maybe 12 minutes. This would be particularly tedious if you want to do multiple tests, and if you think of a process with an even longer delay, perhaps a process with a tank with an incredibly large volume, doing a step test like this would take hours perhaps, whereas doing it in a simulation environment allows us to do step tests for controller tuning in a matter of minutes. So, exporting this data, well rather, once we have this response here, we still need to analyze the results. So from this graph over here, we need to solve, or we need to calculate TD, tau, and our process gain. So from this graph, that's not just quite possible. So what we're going to do is just take this data, import it into Excel, and then do the processing there. So Flownex itself has an Excel reporting environment. All we do is just simply grab a component, open the results section, and then drag that value into the Excel spreadsheet. That value then just gets plotted over time. As you can see, here we have the ball valve angle and the container level. So I'm just going to highlight all of this data. We can copy that out, and then we can put that into Excel. So I've just done that already. You can see this information over here. It corresponds to exactly the same data. We then have our blue line representing our valve opening and the red line representing our level. I've just duplicated the time column a few times. This is purely for processing inside Excel. I'm going to be using the VLOOKUP function, which relies on the column that you're looking up being the left-hand side of the table. So I had to do a small amount of processing using the internal Excel functions and just manipulated my data to achieve this. The actual calculations in the table are relatively straightforward. We calculate our process gain by looking at our minimum and maximum values for our response. In this case, that's the level of the tank, and then the change in our control variable, that was 29, in this case 29 degrees, and we can work out our process gain over here. We then look at calculating our dead time for our process. That one we calculate by looking at the maximum gradient. If you look at the image over here, this line is drawn at the point of inflection on the process value curve. That point of inflection is the point on the curve with the maximum derivative. So I've just simply computed a numerical derivative, taken the absolute value of that, and then using just some of the inbuilt functions in Excel, found the maximum value, then done a small amount of analytical geometry, found out exactly what the dead time is, and then also found out the point at which we reach 63% of our process value, and recorded that as our process time, or tau. With all of this information, I've then used the tuning rules, the COHEN-COON tuning rules, and then according to these formulas over here, calculated Kc, Ti, and Td. All right, then once we have that, it's just a matter of inputting that information back into Flownex. So on our controller, we're going to be switching the controller back to its automatic operation. So this input becomes a 1, and then inputted the terms for our constants. So our proportional constant, our integral time, and our differential time, as we see here in Excel. Once we've done that, we can actually now look at testing our control network. So I want to just deactivate the action that's going to do the step test, and then we can go about testing this controller. So I'm going to run the controller. If we look at the response right now, it was set for the valve opening of 30 degrees, and now the controller itself is trying to get back to its set point. The set point here is 3 meters. If we look at the constant, it's inputted at 3. What that's doing is the controller is now adjusting the valve opening until the tank level reaches the set point. You can see the controller begins to open the valve initially and then slowly maintains that until the tank level flattens out. If you look at our results from Excel, you'll notice that the dead time of the process is 66 seconds with a process time of 103 seconds. So this process, as I mentioned, is inherently delayed. It has a large process delay inside of it just due to the amounts of networks or amounts of systems that are interconnected between our control output and our process variable. So it looks like the system is stabilized quite nicely. So what I'm going to do is make a change to the system. Something I would expect in this type of scenario would be perhaps a change in the demand of supply from the tank. So what I'm going to do is take this valve. Its opening at the moment is about 50%, so I'm going to increase that to 60%. That's going to increase the flow out of the tank. So we should see a sudden dip in the level, as you can see on the blue line here, and then that level should slowly be recovered over time as the flow into the tank increases. So with the sudden dip, because we're using a PID controller, a controller with a differential term as well, the sudden decrease in level, that derivative change, results in an almost immediate response from the controller. So we see the valve opening very rapidly. It opens from about 10 degrees right up to about 26 degrees, and then decreases and then continues to operate at a similar value. This then results in a sudden decrease in our tank level, followed by a gradual increase until its original value. The dip itself only went down to about 2.91 meters, so that's a small change in our overall level of about 0.09 meters. So nothing significant in terms of this process. So from this point, we can look at the system and say the controller does appear to be behaving as we expect and in a relatively fast response as well. We made a change at just before 1300 seconds, and we see it return almost back to the original value by 1500 seconds, back to its original value only a few hundred seconds later. So this controller appears to be performing well. We don't see any oscillations, and this response is relatively fast considering the delay inside of the process. Okay, so as I mentioned, we used the outputs from Flownex with the Excel data to analyze and characterize the process. We then calculated our dead time, our tau, our process time basically, and our process gain. We then used the settings, or we calculated the settings for the controller using COHEN-COON, and then inputted that into Flownex. We then tested our controller. You could run additional other tests, perhaps changing multiple settings around your system at once. Perhaps the inlet steam temperature of your turbine fluctuates over time, and the process and the demand from the tank also changes. You can put combinations of these together using the actions in Flownex, and then see how the controller responds to that as well. All right, so more from a practical point of view, these are just a couple of examples that we've worked on in the past. This over here is a control system for a compressor plant. The system at the top here is the control system, and at the bottom here is the actual model of the compressor plant itself. These are both done inside Flownex, as you can see. The compressors are, the compressor plant is made up of 3 baseload compressors and 1 variable speed compressor, or variable speed drive coupled to a compressor. The baseload compressors just simply operate on or off. These are then coupled to two receiving tanks, which have a line connecting the two of them, and then a supply line out of that. The control system itself is responsible for managing the operation of this plant. The air supply fluctuates over time. As the systems that use this air turn on or turn off or go through different load scenarios. So the actual air supply from here changes, and as a result, the number of baseload compressors online needs to change. To make up the deficit between the on and off values of the baseload compressors, we then have this variable speed compressor. The variable speed compressor is controlled by the PID, and this PID simply adjusts the speed of this compressor until the pressures inside of the receiving tanks are equal to the actual supply pressure that's desired. So with that speed of the VSD, with this variable speed drive compressor rather, we're then able to decide whether or not we need to turn baseload compressors on or off. In this example, what I have here is a reduction in the air supply flow rate. That's this red line on the bottom graph. We start out at a supply of about 5,500 kilograms per hour of compressed air, and then reduce that slowly down to about 4,000 kilograms per hour. This change is made over about a minute, and as a result, we can see our tank pressure begins to increase. As the tank pressure begins to increase, we see our variable speed drive decreasing because the amount of air required reduces. As soon as our variable speed drive reaches its minimum value, the digital control section, through all of these logical operations and comparators and switches, delays, counters, many components all integrated together there, this system itself actually turns off one of the baseload compressors. So that's represented by this green line. It changes from 2 compressors online to 1 compressor online. As soon as that happens, we see the pressure in our tank slowly start to decrease over time. This is because the supplies into the tank is not equal to the demand out of the tank. This then results in a gradual increase in our variable speed drive, which then begins to make up the difference between the supply and the demand of air from the receiving vessels. So it's quite easy to build this control system inside Flownex as well as the thermal fluid network, connect the two together, and then start running tests like this. So you're able to test new control philosophies for the plants, perhaps suggest ways to improve the efficiency of the plant. Perhaps you want to adjust the delays inside of this digital control section to optimize the response time between load changes, or perhaps the receiving the pressures inside of your actual compressed air receivers is not constant, and you want to try and optimize that. You could look at better tuning on the PID itself. So a network like this becomes very practical. The next example I'd like to talk about is an accident scenario. So this is another particularly strong application of this feature, and what we have here is a heat recovery network. It is a supercritical Brayton cycle. We have a heat source on the right over here, coupled to basically the turbine, the line to the turbine over here. This turbine is then coupled through a shaft to a compressor. The compressor, the heat sink in the system is over here into a water line, and then we have a recuperator modeled over here. The 2 valves or restrictors that you see over here represent the turbine control valve as well as the bypass valve. In controlling these 2 valves, we can actually shut the system down safely. So the scenario that we're simulating is a loss of heat on our heat source. In this scenario, what we want to do is first decouple our turbine chain from the generator. So this turbine train with the shaft is set to run at a constant speed. We then disable that and let the shaft calculate its speed based on the power balance between these 2 components. So for example, if the turbine was producing more power than the compressor was consuming, we would have an increase in the speed of the shaft based on the inertia of the shaft, ultimately doing a moment balance on the shaft, calculating the angular acceleration and calculating a new angular speed. This is then used to basically calculate the response of this entire turbine compressor train. What we'd like to do in our shutdown here is ensure that the compressor and turbine slow down in a controlled manner and that the compressor never enters surge. So the graph that you see on the right here is the compressor map, the characteristic compressor curves as you can see, and then the faint red line representing the surge margin. The thicker red line represents the trace of the operating points over time. So it originally started up here on the 3rd line from the top, It then shoots to the right as soon as the generator is decoupled because the turbine train increases in speed very rapidly. It then loops around and gradually begins to taper down towards its zero mass flow rate condition. The control of this is done through the two valves, as I mentioned. We see what we've done in the scenario is put a PID controller to adjust the bypass valve opening based on the surge margin measured in the compressor. In reality, this would be measured more on the pressure ratio across the compressor, or perhaps the actual mass flow through the compressor, and then calculate a surge margin with a small amount of post-processing. Inside Flownex, we fortunately have access to that result, but integrating this into a real control system would just require a small amount of intermediate processing. Another action was also implemented inside of the actual actions manager that I showed earlier, where we did the step test. This was then used to control the position of this turbine control valve, and adjusting this position over time gave us a way to basically remove the power inside of the system. So allow the system to slowly lower the mass flow rates and then shut these compressor and turbine down gradually. So yeah, in this scenario, we were able to look at how the system would behave in an accident scenario. We can look at many other cases, perhaps where our heat source is not lost, and we see a turbine trip, perhaps due to a high bearing temperature. In that scenario, we need to start making changes to other processes and see how the whole system responds in that regard. So you can implement control systems. This is in the design or conceptual design stage, or even in the commissioning stage when you run into problems. So putting together a simulation model like this with both control and thermofluids elements is a very reliable and very efficient way for engineers to start analyzing systems early before they're implemented, or even once they're implemented for the purposes of troubleshooting. All right, so I'd just like to summarize the presentation. Flownex itself offers many features in terms of controller tuning and in terms of plant control optimization. This can go all the way from control philosophy development. This is looking at adjusting control systems or perhaps developing new philosophies for these control systems. This can be for things such as normal operation, or for startup or shutdowns, or upset transients / accident scenarios. We can also look at sizing control elements inside Flownex. I haven't touched on this today. The webinar that was presented last month on valve sizing touched on this, but ultimately what it is we have many different valve models in Flownex, and we're able to model the process as well as the valve itself, and then adjust the characteristics of the valves to ensure that the valve itself can control the process throughout its entire range. We also look at integrated control and process performance assessments. So we can look at accident scenarios, as I mentioned, or what-if studies to try and prove that our plant is safe. Basically, in very strict industries such as the nuclear industry, this is a requirement. So you need to investigate all of the possible failure scenarios and prove that there are mitigation measures / control measures in place that can now handle these scenarios and ensure that they're properly dealt with and that the plant remains in a safe state of operation. We can also look at optimizing our control philosophies. So all of the turbo machinery components have an electrical power result, or have a power result. If we just go across to this turbine, for example, or actually let's grab the pump. This here has an electrical power result. We can look at these, and with a small amount of post-processing, we can sum all of the energy consumptions inside of our network, and then look at the actual energy consumption of the entire system. We can then perhaps graph that over time through different load change scenarios, or through just routine operation of the plant, and then start looking at improving our control philosophies. So adjusting the values on our controllers, or perhaps adjusting delays, or some other digital control parameters inside of our system, and show how that will affect energy consumption. This can then be used to motivate downtime in the plant to rectify the control system, as you can then quantify the energy saving, put it down to a cold, hard monetary value, something that you can convince a manager to approve. There are many other possibilities as well with the Flownex applications. This can be, as I mentioned, testing new control philosophies. You could even go as far as pre-tuning controllers before commissioning. So perhaps you're designing a new plant, you can build the entire control system in Flownex, pre-tune the controllers, and when it comes to commissioning, you give the control engineer a very good estimate of what the tuning value should be. They can implement those and test that the plant works from that point. So it saves a lot of time in doing step tests on your plant or trying to test control philosophies and modify them during the commissioning stage. You can do this instead in the conceptual design stage and shorten your entire commissioning times. As I mentioned, Flownex itself has an incredibly fast solver, so for processes with incredibly large delays, you can then simulate that inside Flownex and save a lot of time or downtime on the plant as well. So yeah, in general, Flownex itself offers many different features that are suited to optimizing your control systems for plants, and yeah, can be quite a valuable asset to both control engineers and to process engineers in industry. All right, that's about everything I have for today. If anybody has any questions, I'd be happy to discuss that.